Hello everyone. So in this supplementary lecture we are going to find how we got this formula. Okay, how we got this VR peak to peak equals VP by FRRC. Okay, this formula. Actually the derivation is quite simple, so you don't need to worry too much. Okay, to find this formula, let me just make a copy of this part of the graph. Okay, so this was our output voltage for a half wave rectifier. The arguments that we will use to derive that formula is exactly the same for the half wave and the full wave case. The only difference will be in the ripple frequency or the ripple time period. Okay, so you can put that in explicitly, and the rest of the argument will be exactly the same. So I am just showing you for the half wave rectifier case. Okay, so the first of all, our peak to peak ripple will be this distance. All right, this distance, this is the upper peak of the ripple, and this is the lower peak of the ripple. All right, so the distance between these 2 points is going to be our peak to peak ripple. This is the formula that we derived. All right, this is the VR peak to peak. Okay, so let me just quickly make some markings in this figure. First of all, what we need is, you can see that our our discharging cycle begins at this point. Okay, this yellow mark point, and our discharging cycle ends at this point. Okay, ends at this point. All right, so and a charging cycle begins at this time and ends at this time. So we can call this short time period, I can name this, I can call it a del t. Okay, simple enough. Yeah, I can call this del t. So for how much time does the capacitor discharge? Well, the capacitor discharges for, the discharging time is delta t. Okay, all right. Oh, sorry, I made a mistake. Delta t is actually the charging time. You see, the charging time begins at this point and ends at this point, and the discharging time is, if the distance between these 2 points in t is ts, the discharging time is ts minus delta t. Okay, it is ts minus delta t. Okay, this is our discharging time. All right, now we need a formula from your 250 days. Okay, those of you who have done 250, we need the formula that, suppose if I charge a capacitor to some voltage V0, okay, and the capacitor starts to discharge through a resistor of value R. Okay, and the capacitance value is C. This value of the capacitance is C. So what is the value of the capacitor, what is the voltage of the capacitor? Let me write this as VCT, the voltage of the capacitor with time. So this is the expression for the voltage is V0 e to the power minus t by RC. Okay, you have probably learned where this expression comes from your 250. It is actually very simple. You just need to write a differential equation and solve this and put in the initial value of the voltage, then you will get this expression. So if you don't remember, I guess you could review some parts of your 250 lectures, and for our purposes you can just assume that, okay, we know this formula. Okay, so what is the value of the voltage at this point. Okay, what is the value of the voltage at this point? Let me call this voltage V1 and let me call this voltage V2. Okay, so what is the value of V1? The value of V1 is, well, V peak, just V peak. You see, this is the peak value of the output voltage. So V1 is just V peak. And what is the value of the voltage V2? Well, we will just use this formula here and put in the value of the time. So how much time has passed after the capacitor has started discharging? Well, this much time has passed, right? This much time has passed. So we will just put in this value. So we can write this as and V0. So what was the maximum value at which the capacitor was charged? Well, the maximum value was V peak, I mean V1. So the value of V2 will be, putting all of these things together, Vp e to the minus Ts minus delta T by Rc. Okay, does that make sense? All right. Okay, so this is the value of V2. What have we put in? V0, we have put in the value of V0. V0 was the voltage at which the maximum voltage at which the capacitor was charged, that was equal to V1, and we know V1 is equals to Vp, so we put in V0 equals to Vp, and in place of T we put in the time for which the capacitor has been discharging. So after the capacitor started discharging, this time had passed, Ts minus delta T. So we put in this value, Ts minus delta T. Okay, now we will have to make some assumptions, some engineering assumptions, okay, to arrive at the final expression.
I think I can.
So note these assumptions carefully. Assumptions. Okay, first assumption is, as you can see from this graph, that the value of delta T is very small. All right, compared to Ts, the value of delta T is very small. In general, we will choose a very big value of capacitor. Okay, so the bigger value of capacitor that we choose, the more flat this discharging part of the graph will become. All right, the flatter will be the discharging part of the graph, and the value of delta T will be even shorter. Okay, so for higher value of capacitors, this value of delta T will be very short, and in general we will choose a high value of capacitance. So the first assumption that we are going to make is that delta T is very much small than Ts. Okay, so if we put in this assumption in this equation, what will we get? We will get that V2 is approximately equal to Vp e to the minus Ts by Rc. Okay, we have just neglected delta T. Okay, all right. Now we are going to do some massaging with or do some playing with this expression. Okay, so probably you remember one expression for e to the power x from your calculus days. Perhaps you remember that we can write e to the power x as 1 plus x square by 2 factorial plus dot 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 many things. Okay, x square by 2 factorial, x cube by 3 factorial, etc, etc. So we will use this expression to expand this e to the power something something term. All right, so we can write this as Vp 1 plus minus Ts by Rc, okay, plus minus Ts by Rc square by 2 factorial plus something cube by 3 factorial and and dot 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 dot. Okay, all right. Now we are going to make our second assumption. Our second assumption is, as I said earlier, that in general, to make our rectifiers work, we will choose a very high value of C. Okay, a very high value of the capacitor. So if we choose a very high value of capacitance, then this value RC, okay, this value RC will be very much bigger than TS, or oppositely we can say that TS will be very much smaller than RC, right? TS will be very small than RC. Okay, so if TS is very small than RC, or RC is very big compared to TS, then all these terms in the brackets, okay, these terms are going to be very small. Okay, TS by RC is going to be a very small term, and if we square that small term, that will be an even smaller term. Okay, that means TS by RC square will be even smaller than TS by RC, and TS by RC cube will be even smaller than TS by RC square, and etc etc and so on. So if RC is big enough, we can actually neglect all the terms except the first term. Okay, we can actually neglect all the higher power terms, dot dot dot. So the second approximation that we are going to make is, this was our first approximation, and this is our second approximation. The second approximation we are going to make is, we are going to neglect all the terms except the first order term. Well, let me just write it as plain minus TS by RC. Okay, well, actually I should have written it as, okay. So we have also found the value of V2. Okay, we have also found the value of V2. Then what will be the value of the peak-to-peak ripple? We have everything at our hand. Now we can write the value of the peak-to-peak ripple. So the peak-to-peak ripple is going to be V ripple peak to peak. Okay, what is this going to be? Well, since I named this voltage V1 and named this voltage V2, then VR peak to peak is just going to be V1 minus V2. Okay, V1 minus V2. Now we will just put in the value of V1 and V2. Okay, so I'm going to write the value of V1, that will be Vp, as we had seen earlier, and this value of V2, Vp minus Vp times 1 minus Ts by Rc. Okay, and if you do the calculation, the final result is going to be Vp times Ts by Rc. Okay, all right. So we can actually write this in another simpler form. We can write this as, if we use the formula that Ts equals 1 by Fs, we can write this as Vp times 1 by Fs times Rc. Okay, so here we have Fs. Why do we have Fs? Because the ripple period was actually equal to the signal period. Okay, that means Tr was equal to Ts. If we had done this analysis for a full wave rectifier, what would happen? Well, for a full wave rectifier, instead of Ts, we would have Ts by 2. Why would we have Ts by 2? Let us see the graph for the full wave rectifier. So this the discharging cycle for a full wave rectifier would end at this point. All right, would end at this point. So what is this value? This value is actually Ts by 2. Okay, this value is actually Ts by 2. So all of our calculations would be the same, just in place of Ts we would have Ts by 2, or in the final formula in place of Ts we would have Ts by 2. So this, for a half wave rectifier we have this is for a half wave rectifier, and for a full wave rectifier we would have Vp times 1 by 2 Fs. Since we would have Ts by 2 here, the 2 would be in the denominator, we would have 1 by 2 Fs times Rc. So this is for a full wave rectifier, and if we wrote these two formulas together we could write them as Vp times 1 by Fr times Rc. Okay, so for a half wave rectifier Fr equals to Fs, and for a full wave rectifier Fr equals to Fs. Okay, in hindsight we could have also in place of using this Ts we could have done this derivation using Tr, then we would directly have this Fr in the final expression. Okay, so we could have done that also, that would have also resulted in the final formula. So this is our formula for finding the peak to peak ripple voltage. Okay, so yeah, so our derivation ends here, and this was all that you had in your syllabus for your rectifier portion. Okay, so in the exam you will be just asked to find the peak to peak ripple voltage. You will just have to put in the proper values. You will put in the value for V peak and Fr and R and C and find the peak to peak ripple voltage. Oh, and another formula that we derived in the last class was the value of the DC voltage. Okay, the DC voltage would be VDC. You see this upper peak, the value of the upper peak of the ripple is V1 and the value of the lower peak is V2. So that we know the average value will be at the middle of V1 and V2. Okay, so VDC would be V1 plus V2 by 2, V2 by 2, and if you put in the value of V1 that we found earlier, this value of V1 and this value of V2, you will get that this is equal to V1 minus VR by 2, as we found in the last lecture. Okay, so this was all that you had for rectifiers in your syllabus. In the next class we will learn about some more applications of diode. Thank you for watching this supplementary video. Well, I guess I should thank you more because you had the curiosity to check how a formula works and how we derived it. Okay, so thank you very much because you are interested in learning about how we derived the formula that we were using. Okay, so hopefully I will meet you in the next lecture. Thank you for being with me. Bye bye.